Welcome, everyone. Let's begin today's seminar. This is my distinct honor to introduce Nihar Shah, who's joining us from Carnegie Mellon University, where he's an associate professor in the machine learning department and computer science. His research focuses on the evaluation of science and science of evaluation. So a really interesting synergy there. His group develops computational tools with strong theoretical guarantees, and they also do conduct controlled experiments for evidence-based policy design for science review. His work has been actually quite impactful. He doesn't just write papers for the sake of writing papers. Their work actually gets used in peer review of well over hundred thousands of papers and thousands of proposals. These are real impacts. And it is probably for that reason that he's been a recipient of many awards. I'm not going to enumerate all of them, just going to highlight a few of them. He's been the recipient of Young Alumnus Medal from Indian Institute of Science, JP Morgan Faculty Research Award, Google Research Scholar Award, NSF Career Award, and the list just goes on. On a personal note, I met Nihar when I was doing an internship in Microsoft Research in 2014. And he always was one of the most spirited and one of the most helpful co-interns that I've had during my internship experiences. And as far as I know, he has kept that spirit of energy and just being helpful and curious. And it is for that reason that I'm super excited that we have him here to talk about his work. Let's welcome Nihar.
Thank you. Thank you so much, Daniel, for the very kind introduction and for the invitation. I'm so excited to be here, and it's been a wonderful morning, despite having woken up at 3 a.m. to beat the lines at the TSA security queue. I work on science of evaluations of science, and a part of my work is on designing algorithms and on proving theoretical guarantees and so on. And the other part is more applied. And today I'm going to talk about the applied part, but offline in our meetings or anytime if you're interested on the theory side, like please feel free to ping me. I'm super excited to chat about these topics. Yeah. And today what I'm going to talk about, I've kind of loosely broken it up into three parts, the good, the bad, and the ugly. And what I'll start by doing is talking about the first aspect. Yeah. So here I'm going to talk about more generally evaluations of AI reviewers, and specifically we'll also hone into identifying errors in papers. So feel free to ask questions, by the way, feel free to interrupt. Yeah. So there are lots of papers recently which are developing AI reviewers or looking to evaluate off-the-shelf large language models in their ability to review papers. Okay. And so the question is, well, how do we do this? And so there are some existing approaches. For example, one kind of an approach is to see how well these AI reviewers match the human reviews which are publicly available, say, on OpenReview. Yeah. Now, here there are a few challenges. For example, one challenge is, well, the human reviews may themselves have problems. Okay. And now what we'll do in the next couple of slides is dig a bit deeper into that point. Yeah. And we'll dig deeper by discussing an experiment that we did in one of our top tier AI ML conferences. And in this experiment, what we did was the following. So we collaborated with the program chairs of this conference, and we created a paper and three variants of this paper. Yeah. Now, in each variant, what we did was we inserted a fundamental flaw in one of the claimed key contributions of that paper. Yeah. Now, keep in mind that these errors were in the main text of the paper. There were no appendices to evaluate. And then the program chairs sent this to a total of 79 reviewers. So each of these reviewers received one of these three variants of the paper. And keep in mind, each variant had one fundamental error. Yeah. And we were looking at, well, how many reviewers identify the errors And then what are other aspects of these reviews? Okay. So we did a bunch of evaluations of these reviews. I'm going to talk about a couple of slices of it here. Yeah. Now, keep in mind that an important limitation here is the generalizability. Like these are three variants of one paper being evaluated in one conference. Okay. All right. Any questions so far?
Um, I suppose it also matters whether these additional errors that we inject, whether they're in the introduction or in the experiments and so on.
Yes.
For now, we are just setting those aside because we are just doing this for one paper.
Yes. So the three variants of the errors were on the methods parts. Yeah. One was in the algorithm itself, a key claim about the algorithm. One was in a way that this evaluation was done. And the third one was highly subtle in a technical proof. Okay. So one was really obvious. One was, you have to read the pseudocode to get this error. The third one was really subtle. Yeah. And what, like, at least our prior when developing this, was that we had thought that the obvious one and the medium one would be detected by a high fraction. And so in order to separate out the great reviewers from the okay ones, we added a very subtle error as well. Okay, any questions so far? Yeah.
Was the subtle error of a theoretical nature?
It was a theoretical error, yes. Question?
There's always some ethics red flags that kind of go up there. So do the reviewers knew that?
No. So we did have IRB approval for this.
Okay.
The way this was done was, and like this is a standard thing that people in other sciences have done, is if the reviewers know that this is an experiment, you know, like there's going to be a Hawthorne effect, right? The change in behavior. So the reviewers did not know a priori. After they submitted the reviews, they were debriefed about this experiment.
Sorry to follow up on this. I mean, implicit here is the assumption that all 79 reviewers did go through proofs, which from my experience is usually not the case. Like usually what we see.
So one of the errors was in the proof, the other two were not like proofs. The other two were, if you see this, you'll know this is an error. One, like the third one, that's why I said, like I thought, at least we had thought that the first two were easy to detect. That's why we added a third highly subtle error in the proof. All right. So now, you know, keep in mind that in our premier conferences, reviewers are very highly overloaded, right? They have to review 6 papers in like 2 weeks or something. And so we'll see what happened here. So our primary outcome measure was, well, you know, what fraction of reviewers identified these errors? So here's what we found. 54 of these reviewers made no comments on the parts that had the error. 19 of them said that this part was sound. They explicitly commented that. 6 people said that this was straightforward, whereas it was actually wrong. And one of them did question this erroneous part that, hey, this looks really fishy. We also did
From which of the three?
yes, this was, okay, the one which was found. That was for the error where you had to see the pseudocode to figure out that the algorithm was choosing hyperparameters based on the test data.
Got it. So this was the middle one.
Yes, that's correct, the middle one. Perfect. Okay, we did a bunch of other analysis as well. One thing we saw, and we have more details in the paper, is that there were very few comments on the methods part. Most of the comments of the reviewers were either in terms of the problem or in terms of the final evaluation. Moreover, we did review quality annotation based on a number of criteria of reviews. And one interesting thing we found was that there was no correlation between the review quality and the self-reported confidence or expertise by the reviewers. Yeah. So the candidate of B was like minus 0.1 or minus 0.002 with a p-value greater than 0.3.
Like the review quality is just only one got it right.
Sorry? Yes. So yes, very good. So this was one aspect. We evaluated the review quality on a number of other aspects. Like, for example, did the reviewer substantiate the claims that they were making and so on? Did the reviewers make any false claims? So on. Okay, so we'll look back to the initial question of how to evaluate AI reviewer performance. And a second existing approach is the following. So you have your LLM review, maybe you have human reviews of the paper, and then you ask other people, either the authors of the paper or other researchers, to evaluate these reviews. Again, there are various challenges. There could be various biases in evaluating these reviews. For example, there could be more focus on style of the review rather than the substance of the review. Now, in the next couple of minutes, I'll dig deeper into this with an experiment that we did in NeurIPS 2022. So this experiment was within the review process of NeurIPS 2022. It was an opt-in, meaning that if you were a reviewer or author or meta reviewer in NeurIPS, you were asked that, hey, do you want to participate? And if you said yes, then you were in the experiment. Okay. Now, in this, what we did was we had a bunch of evaluations of the reviews themselves, and then we asked a number of questions about it. Okay. All right. So the first thing is that many systems, they ask the authors to rate the reviews. So we also did that. And in what I'm going to plot here, the x-axis is the score given by the review to the paper. So the extreme right, that is 10, is a strong accept, whereas the left one is a strong reject. Okay. The y-axis is the score given by the evaluator to the review. Okay. So the x-axis is the score given by review to the paper. Y-axis is the evaluation of the review itself. And again, higher is better. Now, three kinds of evaluators were the meta reviewers or area chairs, other reviewers for that paper, and then other members of the review committee who are not assigned this paper but had a good expertise for that paper. Yeah. And you see that all of them are quite similar. And the fourth bucket was asking authors to evaluate. And we saw this trend.
Did the authors see the scores or only the text of the review?
The authors
The evaluators in general.
The authors see everything. The whole review. Yes. You're right that showing only the text could reduce something, but some of this bias, although I guess some of the text would encode the negative or positive sentiment already.
Yes, I mean, one thing that you could do, I guess, is just ask the authors to evaluate the strengths section or just the weaknesses section without
Right.
seeing the other section.
Right.
If you agree that the strengths are correctly described,
Right.
you agree that the weaknesses
Yeah.
are correctly described, without knowing whether they're overbalanced by the other categories.
Yes. Very good point. I agree. Yeah.
The other, just as long as I'm asking the question, the other
Yeah.
thing that comes to mind is I wonder about instead of absolute scores, relative scores. So when I think about my papers, there are some that I'm especially proud of.
Yes.
They do not necessarily get higher scores from reviewers.
Yes.
And they definitely do not get more citations. They get fewer
Yes.
citations because they're technically harder.
Yes. Yes. And this is an experiment we did in NeurIPS 2021, where we asked authors to rank order their own papers.
Great.
Okay. So I can just briefly go into that digression. In addition, what we did was the following. So you submitted a couple of papers, right? And maybe you co-authored those papers with Daniel. Okay. So we asked you to rank order your papers. We asked Daniel to rank order his papers.
Yep.
And now there are two papers which you both have co-authored. So now we can compare Daniel's ranking on those two papers with your ranking on those two papers.
Yep.
Okay. So now what we did was we compared how consistent are co-authors with each other's rankings as compared to rankings given by the authors versus the reviewers.
Fantastic.
Same consistency. Okay. The co-authors agree, I think 66% of the time, and authors versus reviewers, the agreement is 64% of the time. I might be missing 1 point here and there, but it's almost the same. This was in 2021.
One of the controls for the green line would have been to simply give them the numerical score and see what they think.
Yes, that's another possible control, and probably the bias would be higher.
Yeah, that's what I'm thinking.
Yeah. Great. So this was an overall score, but we just didn't ask an overall evaluation. Before the overall evaluation, we also asked each evaluator to evaluate along specific criteria, like did the review exhibit an appropriate understanding of the paper? Did it cover most parts of the paper? Was it substantiated? Was it constructive? And we observed the same thing everywhere.
Question. I guess I guess the conclusion here is that authors are biased toward reviews that are more
Perfect.
But I guess a skeptic may say that authors, it's possible that authors are actually right because they best understand their own paper. It's other raters, the orange, blue, and the red trends. They're written by other people who have no stakes in the problem, and perhaps their reviews, their annotations are quite sloppy.
You're right, and this could be true, that could be true, we don't know. And so now if you're using authors to evaluate AI-generated reviews and compare with human reviews, we don't know if this bias exists or not, right? Maybe this exists. And so you have to, like, if you're making a conclusion about that, you have to ensure that this bias doesn't exist. That's the whole point. Yeah. All right. So now, well, authors are biased, okay. But now what about other reviewers or meta-reviewers and so on? Yeah. So now here we did the following randomized control trial. So this was the review form for NearEPS 2022. It had 3 text boxes and then a bunch of drop-downs. Now what we did was the following. We took a bunch of reviews and then we made them twice to thrice as long without adding new information. Yeah. So specifically, we would copy the summary into the strengths and weaknesses as well, making it longer. We copy pasted the abstract. We would copy paste fluff text, like now I'm going to review this paper, blah, 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 things like that. And we copy pasted this text from the drop downs here. Yeah. So we did a bunch of these copy paste and adding of fluff text. And now we were looking at, well, how does the evaluation of reviewers, meta reviewers change? And so whenever an evaluator came in to evaluate the review, we either showed them with the original review 50% of the time or the uselessly elongated review. And what we see is that the mean score significantly increased. And this was true not only for the overall score, but across all of the individual criteria as well. Any questions?
This is the score assigned by who?
This is the score assigned by the evaluator, that is another reviewer or meta reviewer, to the review.
Well, now we know all how to win real robots.
All right. So again, I look back to how to evaluate AI reviewer performance. And this meta level comment is that there are these various approaches towards doing this. I think all of them have their pros and cons. And so what we have been looking at is a slightly different way of doing it as compared to the references I said, where our approach is to focus on the objectives of peer review. Yeah. And today, journals and conferences kind of look at 2 key evaluative aspects, which is ensuring that the published research is correct and whether it's interesting or better research as compared to other things. Yeah. So I'm very briefly going to talk about a few things, a few tidbits on the rigor of published research. So we discussed this experiment with human reviewers, and after doing this, but before releasing these papers in the public, at that time GPT-4 was the main model, and so we tried if GPT-4 could find the errors. Yeah. And the prompt was very simple. It was just that identify if there are any key errors here or not. And what we found was that the obvious error we thought was obvious. It was identified consistently across many, many runs every single time. The subtle error, the medium error, which the reviewer had identified, at least GPT-4 was not able to identify with just the standard prompt. But if you steered it, that is specifically asked it to look at that part, then it said, oh yeah, here's the problem. The subtle error it was never able to identify. So there's some comparison between human and LLM reviewers on this aspect. We also did a little more, that is, we constructed another data set of short papers. Again, at that time, it was GPT-4. And we had deliberately inserted errors there as well. We were checking if LLMs can find these errors or not. And they could identify the errors in about 50% of these short papers.
This is with or without the steering.
This is without the steering. This is absolutely without steering. Yes. And these errors included mathematical errors. For example, implications of one way of convergence of random variables onto another way of convergence of random variables, or conceptual or logical errors, like there's a Simpson's paradox going on, because of which the paper draws a false conclusion. Yeah. So this at least provides some evidence that there is promise in using LLMs to identify like key fatal flaws.
Quick question. The errors that you introduce, are the papers otherwise sound? Like I can imagine like a derivation where there's a mistake, but then the proof would still be otherwise correct.
Yes.
Versus an error that actually like invalidates the result.
Yes. If we did not, before incorporating the errors, right, like what we did was we sent this to a number of experts in the field to evaluate, and they said it was sound. I mean, of course, we also evaluated. So that gives us some evidence that this is sound. Moreover, after inserting the error, we deliberately inserted the error such that a key claim in the paper, which was mentioned as a key contribution, that got invalidated.
Sorry, I'm a little confused about that. So it sounds like the claim might no longer be supported, but it was still true.
Oh, no.
Which I think was.
Oh, sorry. So the claim
like
was
you would
not,
have to change the polarity of
sorry.
the.
So the claim was not true at all. Like for example, like one error, the subtle theorem error, the theoretical error was a necessary, like a claimed necessary and sufficient condition for identifiability of a statistical model. The claim itself was false.
So that claim was not in the original paper, and you had to insert it.
No,
the original paper is correct, right?
Yes, the original paper is correct, but the original paper would not have this condition as the necessary and sufficient condition.
I see. Okay, thanks.
All right. So I'll move on to the second topic, which is on vulnerabilities of reviewer assignments to fraud. Okay. And in order to go in here, I'll give you two pieces of context. One is about fraud in peer review, and the second is about reviewer assignments. So let me start with the context of fraud. And in particular, I'm going to tell you about two types of fraud. The first type of fraud is on fake accounts and identity theft. So what do I mean by this? Yeah. So let's say you are a program chair for a conference, right? A top conference. And a reviewer, Daniel Khashabi, signs up to review. Okay. With the email address khashabi.daniel@ghu.edu. Okay. Moreover, you round-trip verify this email address, meaning that this email address actually exists, it's not spoofed, and this person has control of this address. Yeah. But this person has nothing to do with Daniel or Johns Hopkins. It's some random person sitting somewhere else in the world. And now this person signs up as a reviewer or a meta reviewer, and then tries to get assigned their own paper or their friend's paper for reviewing, and then tries to accept the paper or even nominate it for the best paper award. Yeah. And we found 94 such fake profiles in open review in a recent investigation, where they were trying to sign up as reviewers in NeurIPS, ICML, and these top conferences. This is one kind of fraud. Any questions?
How did you find this?
Yes, so there were a bunch of things involving IP addresses and duplication of profiles and a bunch of different things. And then we verified that, I know, for example, I know Daniel, I know his real email address, I can find it from the university website and ask him, hey, is this your email address? And say, hey, I have nothing to do, I've never heard about this email address, and so on.
How did the fraudsters get these verified email addresses?
Yes, how did
Sounds
they?
like universities need to raise their security.
Yes, universities need to raise their security bars. So I worked with, this affected a number of top universities, and I worked with their IT departments on this. And what we found was the following, that the fraudsters would gain access to one or few email addresses from that university, either through a phishing attack or potentially someone from that university selling their email address. And then they would create aliases in the names of other people in that university, and then use that to do this.
Their nickname is Kashavi Daniel.
Exactly. All right. The second kind of fraud is collusion ring. So this is where groups of researchers will make pacts saying that, hey, why don't you try to get assigned, why don't you try to get assigned my paper for review and then accept it. In return, I'm reviewing your grant proposal and I'll accept yours. Yeah. And this has become a major problem in many of our conferences.
How come I don't get invited to these things?
Maybe those emails go to your spam folder. Take your spam folder. All right. So this has been a major issue in many of our conferences. And you see, in both of these fraud, one key component is that the dishonest reviewer tries to get assigned a certain target paper for review. So now let's look at this reviewer assignment. Okay, let's look at the second piece of context. Now, in order to do this assignment in all of our top conferences, this is done in an automated or semi-automated fashion. And this assignment uses two key pieces of data. The first key piece of data is text matching. Okay. So for every submitted paper and every reviewer in the reviewer pool, you take the text of the submitted paper, the text of the reviewer's previously published papers, which is called the reviewer profile, and then using NLP, you match that. Okay. So for example, Open Review uses the Spectre set of models, which are found to be the best performing in various evals. Okay. The second is reviewer bidding, where if you are a reviewer, after the deadline, you'll be shown the list of all submitted papers, and you can say, hey, I have expertise or interest in reviewing these papers, but I don't have expertise or interest in reviewing these other papers. Okay. Any questions? Now, what's done after this is, using all of this data, now you run an optimization problem that assigns reviewers to papers so that the text matching similarity or the reviewer bids are maximized. Any questions? All right. Now, this bidding process is known to be highly vulnerable for such fraudulent attacks. Okay. For example, if I want to get assigned a target paper, I'll say, hey, I have interest and expertise in reviewing this paper, but I don't have expertise for reviewing other papers. Cool, I get assigned my friend's paper. Yeah. And so this bidding process has been the focus of a lot of past research on how to make this bidding process more robust. Yeah. Moreover, some venues like CVPR, ARR have completely banned bidding. They use just the NLP text matching. Yeah. And they assume that the text matching is noisy, but at least robust to gaming. That's the underlying assumption. For example, some of the papers, they assume that the text matching is noisy but robust, and then use some bidding data to reduce the noise. And in ARR, CVPR, they're only using the text matching. So the key question is text matching safe from manipulation? This is the question that we ask. Now, I'll be brief in the next part. So we look at a number of attack vectors. So one is the authors can modify the abstract of their submission. For example, if I have a computer vision paper and I want to get assigned somebody who's doing self-driving cars, I can just write self-driving car as a motivation for my work. A second attack vector is that most conferences allow reviewers to update their profiles. So they have, like, let's say you have 20 past papers, and you can select which papers you want to keep in your profile for this conference. And third thing is access to publicly available past data. For example, in iClear, you have all the previous year's papers publicly available. You have the list of all reviewers from the previous years publicly available. Yeah. So what you can do is train your attack on last year's data and then try to use it this year. And it turns out that we found a very high correlation between the success last year and then this year. So if you train from last year and you get a high success rate, there's very high chance that even this year you'll be highly successful in the attack. And so we use these three attack vectors. And so here are some manipulation success rates. So the 3 rows that I'm going to show you. Yes, question.
The third attack. So
Yes.
what is what attack am I honing based on previous year's data? So
Yes.
the first 2 that I'm going to modify.
Yes.
So I'm going to pretend that I had a paper last year,
Yes.
and I'm going to try and write this year's paper. I'll pretend it's last year,
Yes.
and I'll start modifying my abstract
Yes.
so that and my friends, like Jason's reviewer choices,
Yes.
so that paper will get assigned to Jason. That's what I'm
And
going
last
to
year.
last year.
Perfect.
Okay.
Perfect.
That's okay.
But how do you actually, you can't rerun last year. So how do you hone the attack?
Well, we can do that because last year, iClear, for example, the papers are available online and the reviewer list is available online and the assignment algorithms are available online.
I see. So I run my own copy of Spectre.
Perfect.
I get all the reviewers' profiles, and I don't necessarily know what they do with their sub-selections, but I don't sub-select.
Yes.
So, okay.
Yeah. Okay. And so here in this evaluation, what we did was the following. So we would randomly sample a paper, and then we would look at the reviewer who was ranked 101, 501, and 1001 for that paper when trying to compute the similarity without any manipulation. Yeah. Now what we saw was, well, when you actually manipulate it, how much does this increase, this ranking? And can we get this reviewer to be in the top 5 or something for this paper? Yeah. So we look at top 1, top 3, top 5. And turns out it's a pretty decent rate of success, where even if the reviewer was originally 1001, about more than 50% of the time, you can get them in the top 3.
Here, the levers of manipulation is modifying the abstract.
Modifying, so yes, so we did various ablation studies, but modifying the abstract and modifying the reviewer profile.
I see. And maybe if you can also comment on like how much effort did it take for you to get them to this point?
Yes. So actually, so this is now done in an automated fashion. This was like large scale evaluation where we did automated modification. So that's like a few calls to an LLM.
So basically just revise, like just try multiple revisions and pick the best one.
That's correct. That's correct. And it was constrained so that it has to still match the same content as the original abstract.
And these numbers are so I guess the optimization was done on past year's data. And these are on like future data.
Perfect.
Yeah.
So the optimization was done in 2022, and this eval was done in 2023.
Yeah, so you didn't talk that much about manipulating the profile, but I was wondering whether it's possible for, like, suppose I want to review somebody's paper, could I post a very similar paper on archive to make it look like I'm an expert in that area?
Yes, absolutely. That's
And then also, if I want to review my own paper,
yes.
like I already have written other papers in that area, and if I can just claim that I'm a different person, then maybe I can manage to review it.
Absolutely, yes. And in fact, like many conferences allow you to upload a PDF into your profile. So you need not even upload to Archive.
Wow.
You can directly upload it here. That makes these attacks super duper easy.
Yep.
And here we assume that, well, that's not allowed. And we just wanted to, like, this was, assuming that those restrictions are already there, because that makes it super easy. We just allowed modification of an existing profile.
Okay, so it's even worse than your side here.
Yes, that's correct. In practice, it can even be worse. Yes. Yeah. We also then proposed and evaluated a number of ways to mitigate this issue. I won't go into the details because this needs some background of how the open review system works. But like these are now deployed in open review, and many conferences are already using it. So if you're a program chair for an upcoming conference in open review, yeah, consider making your assignments robust as well. Any other questions before I move on to the third topic?
Is there, maybe this is already considered here, but like, is there also a consideration on making sure that you don't over optimize the paper for a particular reviewer? Like,
Yes.
if you're close enough, then that's good enough. The rest can be randomized, right? You don't have to really be very close.
Yes, that's a very good point. And the way we ran the optimization was that you want to come close enough to this reviewer, but you don't want to move too far from the original abstract in terms of the content. So if you're already close, you're already there, and the algorithm will take fewer iterations.
So this is a different kind of risk than manipulation. But given that the algorithms are publicly available that I can run on last year's data, can I also find out who reviewed my papers? If these mitigations like percentile pooling or not? Like,
yes, that's a very good question. And I don't, I don't know how much some specific technicalities of last year's systems, like how the reviewers last year subsampled their papers and so on, how much that will affect the
I mean, there was an
actual.
optimization algorithm involved, and so I'm not. But
But
if I
there-
could just narrow it down to 20 people or something, I could do stylometry.
And you could do that.
You were the one who wrote that review.
You could do that. You could do that. Yeah, because the reviewer information, the paper information is all available online.
But supposedly these modifications actually mitigate that concern, right?
To some extent.
These modifications. So these modifications.
The first one.
So this would mitigate that, like, if you were to modify your own profile, like, it won't change the assignment too much. I don't know if it will mitigate the concern that you're raising.
Well, the
We can think
percentile
of it.
pooling makes it harder to identify. I mean, it adds some
That's just,
specificity.
yeah.
So it's harder to identify the review.
Yeah.
Quick question. I was wondering if there's a side effect of is like courseware matching having an impact on the quality of the reviews? Is that like not?
Yes. So it's hard to measure the quality of the reviews themselves because as we discussed, there are various biases and so on, but they do have ways of measuring the affinities, the matching, and we do see going from max to percentile, there is only a small change in the affinities quality. All right, I go to the third and final topic, and this is about autonomous AI scientists. And so there's increasing prevalence of these autonomous AI scientists, which you give it some broad direction, and it can do all of the research, including generating a paper. And there are a number of labs or companies that are developing these autonomous AI scientists, and I think that their prevalence is going to just increase more and more. Yeah. Now, papers written by these AI scientists are already accepted to the ACL conference or ICLR workshops. So I think they're here to stay, whether we like it or not. And so the human researcher would give it some broad direction or a task description. And then the AI scientist would generate a hypothesis, develop some algorithms if it's in the ML field or computer science field. It'll get data, evaluate, and then it'll write the paper for you. Yeah, that's broadly how it works. Questions? All right, so they are following this entire research workflow. And the question that we asked is, well, are these workflows methodologically rigorous? Okay, scientifically rigorous. That's the question we asked. And in particular, we investigated 4 potential pitfalls, which I'll describe in the next few slides. All right, so before describing the potential pitfalls, I'll give you a higher level overview of the methods. One key point is that we really wanted to identify if this specific issue is happening or not. And if you were to just take, tasks that are commonly done or data sets available on the internet, it leads to a number of confounding factors, okay, through which we can't really identify this issue. And so in order to eliminate confounders, what we did was we created our own task. This was a novel task, which the best of our knowledge is not there in anywhere on the internet. This was a binary classification task, which we call symbolic pattern reasoning. And then we had a controlled experimental environment where we could change various aspects of this task in order to measure specific questions. And we were able to, we evaluated 2 open source systems. These are very popular open source systems, Agent Laboratory and the AI Scientist version 2. All right, so the first potential pitfall we investigated was inappropriate benchmark selection. Okay, so what do I mean by that? So let's say that you've developed a new model, right? And now you want to do an evaluation and report the evaluation. Right? On the internet, there are lots of different data sets or benchmarks that you could use. Right? And somehow you have to choose some subset of them that are representative for your task, maybe diverse enough that it will capture various aspects and so on. Right? Somehow you have to choose a reasonable subset. And so the question that we asked is, do they simply select benchmarks so that they get a better performance? That's the question we asked. The question on the question? All right, so here's our experimental setup. We constructed 20 synthetic data sets that spanned 5 difficulty tiers. And now these were 20 data sets. These are too many to report in a paper. So we would ask the AI scientist to choose 4 of those 20. And then for each task, we also told it what the state of the art algorithm's performance was. And remember, these are like across 5 difficulty tiers. So for more difficult tasks, the SOTA was lower. Now we also obfuscated the dataset IDs, so that just by the IDs, etc., they can't figure out what dataset it is. Also randomize the order in which these 20 were presented to them. And now the question is, well, do they select easy tasks or not? So for Agent Labs, what we found was that we did not find any dependence of the benchmark selection on the difficulty. However, about 80% of the time, it would just pick the first 4 tasks. So maybe ideally you would want to have a diversity in terms of difficulty or something, but you just pick the first 4 tasks.
Question. So all of these tasks are the made up
That's
tasks.
correct.
And how do you communicate the task difficulty? Is it just articulated in plain language there?
So the task difficulty is through this SOTA reference. So we are not telling it that, oh, this is easy, this is hard. We are saying that the state of the art on this is 52%, on this it's 96%.
I see.
Do the system actually know like the correlation between like other like factors that were really looked on, like basically how representative this task should be for the question you posed, where it only knows that.
Right. So here the representativeness is only in terms of the difficulties. So ideally, if I had to choose 4 out of those, I would choose 4 with different difficulties. That's what I would have done. And so that it shows my performance across the spectrum of difficulties. And that's the only diversity that we put.
Human authors, what's choice? It's here. That's in a similar experiment.
maybe. I don't have evidence to support or refute your claim. But like, you're making a very good high-level comment that some of these pitfalls would also be there in human authored papers. Right. The challenge is that the AI scientist systems now can do all of this much more at scale and much faster. And so that's the challenge. The good thing is we can actually probe the AI scientist systems to figure out if this is happening or not. Whereas it's harder to probe the human researchers' work and their brains.
Yes, one question, and I'm thinking about how I might choose a data set, right? So do these data sets have some metadata describing in what way perhaps they're different? Because what I'm thinking is, based on this process of generating a hypothesis and then evaluating it, the hypothesis might have something to do with the metadata, right? You might want to say this works better when the images are out of focus, or this works better when there is backward. Pick a criteria.
Right.
So was there anything like that, or were these just flat?
These were flat data sets,
Okay.
and the only distinguishing information apart from the data set was the SOTA reference.
Okay. So then I guess the AI scientist wouldn't have a methodological reason to choose one data set over the other.
Yes, except for maybe you would want to show what happens across the spectrum of difficulty.
That would, of course, be a good thing to know otherwise.
But otherwise, no, this like it works whether the image is in focus, out of focus. Yeah, that's not in scope of this experiment. Great. So yeah, Agent Labs chose just the first 80% of the time. What about AI Scientist V2? So in this table, the rows are along the task difficulty, easy to extremely hard. And this column is without the SOTA reference. So we did two things. In one set of experiments, we did not give it the SOTA reference, just the data sets. And the other, we gave it the SOTA reference, just to see how its behavior changes if it does. And what we found was that without SOTA reference, it chose uniformly at random across the difficulty levels. Whereas with SOTA reference, there was a significant bias towards selecting the easy task difficulty. That is where the SOTA was high.
Does it matter how high the SOTA reference is?
Like
it might be rational that if in fact the state of the art is doing quite poorly, then you might want to choose an easier set so that you can get some signal to make progress.
Yes, so in this case, but poorly subjective, but in this case, the SOTA in the easy case was pretty high. Yeah, so I wouldn't like.
Right, you get SOTA references for all of these.
Yes, we gave SOTA references for all the tasks. Yeah.
But then there's a question, I guess my question still stands. What happens as you shift them up and down?
Yes.
Like maybe it's always picking one where it thinks it could get about 80% because that's where you think you might be able to make progress.
Yes.
It's like got some traction, but there's still a lot of errors.
Yes, I don't know the answer to your question. Yes. The second issue that we were looking at was data leakage. That is, in practice, when we are doing research, well, we are using certain data sets online, and very frequently the test data is also available online, right? But of course, we are not supposed to look at the test data until the final evaluation. So what do the AI scientist systems do? Do they peek at the test data or not? That was the question that you were asking. So a lot of the processes of the AI scientists are opaque, and therefore we can't really get to this very clearly. But what we'll do is we'll use a specific way to get to it to some extent. Okay. So here's our experimental setup, which is inspired by this paper by Echenick and Hay on a different problem of investigating p-hacking. So what we did was we created noiseless data sets where we had a deterministic mapping from features to labels. And then we injected randomness in the labels. So this was just random Bernoulli noise. Yeah. So you can't do anything better than 1 minus noise level unless you overfit to the training, to the test data. Yeah. And so we're checking if the reported accuracy is more than 1 minus noise level. Yeah. And by the way, we gave it the SOTA 1 minus noise level. Again, what we found was that in various cases, the AI scientist systems could get 1 minus noise level accuracy. Sometimes it would even report 100% accuracy on the test data set. Okay, so that's not possible because we had inserted, say, 30% noise, just random noise. So we started looking deeper into what it's doing, and we found something surprising, something unexpected, that in each of these cases where it's getting a higher accuracy, it was not looking at the test data. Yeah. It was either subsampling the data set in some fashion, or in many cases, just cooking up a new data set, which is a completely synthetic data set that it has cooked up. And then it would report the performance on that cooked up data set. Yeah. But in the paper that it writes, it never mentions that this was on the cooked up data set. Okay, so it reports as if it was on the original data set. Okay. Any questions? So the third potential issue we investigated was metric misuse. That is, often we have multiple possible metrics through which we can evaluate our methods. And so the question was, well, do they selectively choose a report evaluation metrics where their performance seems better? So in our experimental setup, we again constructed a task where we had two metrics, and through symmetry, both of them were equally okay. But we constructed them so that on the data, one of them would have a better performance than the other. We were seeing, does it choose the metric which has better performance? Turns out, no, we did not find any evidence of metric misuse. Finally, the fourth and final pitfall we investigated was a post hoc selection bias. Okay. So what do I mean by this? So recall that the AI scientist system is given a broad direction, and it does all of these things and gives you a paper. Right? But internally, there is something specific that happens in all of these systems. That is, it does multiple runs of each of these, and then it selects one of them to report as the final paper. And so the question is, well, is it true that they'll have multiple runs, for example, on the test set, and then just pick the most favorable result, which will precisely be p-hacking. Right? So does the AI scientist system p-hack by evaluating multiple hypotheses and picking the most favorable one?
Well, this is not necessarily unfavorable, right? Because you might have different versions of your statement, and you might pick the one that is the most well written. So it's not clear that this is necessarily equivalent to p-hacking.
Yes. So I'll tell you the precise thing that we measured in a minute, and then you can ask me again if you're not convinced. All right. So here's our experiment design. We first got the AI scientists to generate a number of machine learning research projects. And now we manually varied the test or training performance that it got in each project. Yeah. And I'll describe in a minute how we varied this. But then we were looking at which of the projects is selected by the AI scientist. Okay. And does it depend on the test data? Because that's the problem we are looking at. It should not depend, the selection should not depend on the test data. It should depend on, say, the validation of the training data. Right? Does that clarify your question? Yes. Yeah. And so I'm reporting the results for AI Scientist V2. We had similar results for the Agent Lab. Now I'm going to show you 5 rows. The top row had research projects with the best training and the validation performance. And then you go down and come to the worst training and validation performance. Now we'll have a control condition where the top row would also be the best test performance. The bottom row would be the worst test performance. Yeah. So in control condition, top is best test and training and validation. This is worst train test validation. And finally, we have a manipulated condition where we change the test performance value. So the top row is the worst test performance, but still best training validation. The bottom row is the best test performance and the worst training validation. Okay, questions? So now if the choice of the project was not dependent on the test data, then the values in this column, that is how many times was this chosen, etc., should be similar to the values in this column. So what we found is, well, in the control condition, when the test and training were correlated, you see that in most cases, it would pick the one which has the best training validation test performance, which is intuitive, which is natural. But now here we flip the test performance. Ideally, this should be similar to that. But we see that there's a significant change. That is, now it's picking the ones which has the best test performance most frequently. All right, so this is doing p-hacking on the test data. All right, and finally, so one remedy that we propose is the following. So we developed a simple LLM-based classifier, with nothing really fancy, with handcrafted rules to detect these 4 pitfalls. And I'm going to show you the evaluations, but for that, like, one piece of context is that today's conferences evaluate primarily the submitted paper. And so we evaluated these pitfalls using these LLM classifiers. Again, just a simple prompt. And using this submitted paper alone, which is the final paper generated by the AI scientist, this was a classification, uniform classification, so random is 50%. And we get about a 50% accuracy and approximately 0.5 F1 score. So we can't really detect these issues from the final paper alone. However, then we gave the LLM the paper, the trace logs of the entire workflow, and the code generated by the AI scientist, in which case we can improve the accuracy to 74% and the F1 to 0.75. This suggests that the trace logs and the code do contain useful information that can be used to identify these pitfalls. Right, so a key actionable takeaway is that if your conferences tomorrow are going to admit AI scientist papers, and there's one conference that's already doing that, should also ask them to submit detailed trace logs and the code as well, not just the paper. So overall, we went through good, bad, and ugly of LLMs in science. And for me personally, a key takeaway I've been working here is that LLMs present great opportunities, also challenges. And whenever we're looking at these problems, we'd like to think about them from what are the first principal objectives of science, and let's build from that. With that, I'll stop here. If you're interested in a peer review, I have a survey on peer review, which I regularly update. And I'm very, very happy to chat with anyone who's interested. So please send me an email. Thank you.
Okay, yeah, for a couple of questions.
One very quick comment. Fantastic talk, right? One could envision a malicious player that would take good, bad, and ugly, combine them in 5 years, create AI scientists who would write key papers, apply together, play, review each other's paper, and win the best paper award. Do you think it's possible?
Yes, it is possible. Yes, you could. What you're saying is, you could have AI systems infiltrate the reviewer side through various such tricks, and then submit papers, and then somehow get signed and get a best paper award. Currently, there is at least some manual oversight which hopefully will prevent it. You have these program chairs and best paper award committee at least for the award case, but yeah, you're raising a good point. It's entirely possible.
Well, they'll probably start having their own peer-reviewed conferences.
They had one, right? There was one conference which folks at Stanford started where only AI scientists are allowed to submit and then LLMs will review. And I don't know who'll attend, but
It'll be cheap because they would have to travel.
yeah.
I'm wondering if you have any thoughts on the submission of LLM-generated papers to conferences. You know, even besides the Stanford menu, like all other menus, there's no way to verify to what extent the
Yeah.
paper is written by LLMs, right? You just submit a PDF.
Yes, and that's been a big challenge for all the conferences and journals that they are getting there's been a significant increase in submission of AI slop. I think a year or two ago it was easy to identify that, oh, this is just AI slop, but now it's become much harder. Yeah, and we've received a lot of submissions where on the face of it you'll think it's a genuine paper, but when you actually go through it you'll realize it's not saying anything. And I agree, it's a big problem and we don't know how to address it.
I was wondering
I'll complete, yeah.
okay, what are your thoughts on like the tasks that you choose to work on in the space of AI for reviewing, and whether they reflect what authors want and need and what is useful? So you talked about writing the review or spotting fraud in assignments. But I was thinking it's just such a rich space with so many tasks that we could work on that would be really helpful, like surfacing experts to consider, assisting with assignments in better way. So yeah, I just wanted to hear from you, what are your thoughts on how to choose specific tasks?
Yeah. And you're making a fantastic point that there are like so many dimensions to this scientific workflow and peer review process. And if you want to optimize, like which ones should be optimized for, right? At least my personal perspective comes from speaking with the many program chairs, authors, reviewers, as well as the platforms like Open Review. And I regularly try to speak with all of them to get their feedback on what they think is most or least important. And some of the things have been inspired by this. So, for example, fraud and collusion ring is one of the top headaches of program chairs. This is something they really want to mitigate, because even if there are a few papers that are fraudulently accepted, it creates a very negative vibe in the entire community, right? So that's how that was inspired. But yeah, more generally, like I'm very happy to chat offline, I guess, about like specifics of anything else. Like I like spent a ton of time speaking with a lot of stakeholders, just to understand their challenges. I'm very happy to chat with anyone offline. Yeah.
So I think this is a great part. So at least most folks on AI research or sales research and their confidence sales conferences. I was wondering what is big with stakeholders, how does it generalize to other domains in natural science? And in those cases, maybe you cannot really, in CS, you can have AI generated code and experiment, but in other domains, maybe still have more physical side of the research. They cannot have AI, but AI can have other things as well in the process of research and writing papers.
Yeah.
So how to generalize to
Yes, that's a great point. So I'll start by saying that a bunch of things that we've done in computer science for peer review in the last 10 years, right now, people in biomedicine, astronomy, etc., are reinventing the wheel. Yeah. So in the last 2 or 3 years, I've seen a bunch of papers from there, which are doing something very similar to what we had done in 2012, 2013. And so they are also facing very similar problems, at least some of these communities like biomedicine or astronomy. And so, that the solutions do translate. In fact, we've had a very nice collaboration with people in astronomy, where for peer review, they're using algorithms which are initially designed and deployed in ICML, etc. And it's worked very well for them, and they're extremely happy. And, likewise, for the AI scientists, I think the initial AI scientist systems were developed for ML research, this fully autonomous AI scientists, but I think they've started expanding to other fields as well. Right now, it's not using hardware, but it's looking at any problems which can be done with data online. So I think a lot of this does translate to many other fields.
more question here. To what extent do you think that some of these issues with like peer reviewing and AI is stemming from the way we have designed the medium of scientific publication? Like, traditionally you write a PDF. The code used to be optional. Now increasingly, I think that's mandatory, and it's perhaps a lot of these design choices for like how you write paper were like design choices that were made a long time ago that perhaps need to be revised so that they meet the demands of today with all of this AI automated generation.
Yes, that's a very good point. Like the systems that we have for reviewing, etc., were designed long time ago and not keeping AI generation in mind, right? And so right now, like especially in biomedicine, they're facing this acute problem of fraudulent papers. And there are some initiatives where what they're doing is the following. So they're worried about papers which claim that it did this experiment, but it didn't actually do any experiment. Everything's fabricated. And it's very hard to figure it out given Gen AI. And so now what they're doing, there's some initiatives where they're looking at the question that for experiments that involve hardware, can we in the hardware have a way to embed public key cryptography so that any images, any data generated by the hardware is accompanied by a hash that now publicly can be verified that it was actually generated from that machine and not cooked up. And so these are things that changes are happening in response to this AI slop.
Okay. Let's thank Nihar one more time.
Thank you.
And if you have any other questions, we might have a few minutes to come here and talk to me.
Thank you so much. Thank you. Hi, Sanjeev. Yeah, I'm leaving for dinner.